Hello. So today we'll see how data structures actually work behind a production AI system. In this session, we will give it a query and travel through 8 real pipeline components with interactive visualization experience. So first, when we give a query, the first job of an AI system is to, uh, you know, do an intent routing. Figure out that what the query is about. Is it about like weather, coding, doing a research, anything about booking, or a general default queries. So for this, first as soon as a query comes in, we have a try data structure. Try data structure is nothing but a specialized tree-based data structures used to efficiently store and retrieve keys in data set of strings. So for example, try data structure looks like this. It has a root node, then the following children nodes are nothing but a characters. As you see here, an empty node serving as a universal starting point. The edges and nodes are each downstream link represents a character, and there is a third part to it which is a boolean indicator that this is an end of the word, making whether a complete word terminates at that node. For example, imagine we have a list of characters saved in our try data structures, weather, book, code, journal, bill, or billing. Now our query contains something about bill, so it will create a list of intents that this query contains a bill and billing thing. So it will give this list to our hash map to look up in its table to see if that billing agent is there or not and pass it the query. For example, in our scenario, we have a weather intent. So we'll give a weather prefix which will search in our try data structure, which will return a list of one input as a weather, which will be mapped in our uh, hash map. Hash map is nothing but a dictionary data structure. So it will look in the hash map and it will see, yeah, that weather is matching with the weather agent, and it will dispatch the agent over there. All of this happens in time complexity of OM plus O1 of hash map. OM is nothing but the length of the character, because we have to look characters one by one in our try node, and O1 is to look up the hash map. In practice, many real systems starts even simpler if keyword in text or regex. A try only becomes necessary when you have many overlapping prefixes. So many systems like Claude and ChatGPT and Gemini uses try data structures for this. If you see real frameworks, LangChains, router chain, Dialogflow, then IBM Watson, all uses AppMap style dispatch under the hood. LLM based routing is possible but costs tokens. Rule based maps are faster and transparent. This is the code over here. So if you can see, this is the hash map or dictionary. This is our try node data structure, and this is query routing. This is how an intent is. This is how we figure out the intent. The second is session memory. For this, visualize that you have a queue of maximum 5 sizes. Here we use DQ plus LRU cache. DQ is nothing but a queue, but you can pop items from both the sides, from head and tail. So imagine we have a queue of 5 indexes. Our fifth index is empty. When we send a message, our queue becomes full. When we send a new message, the last item of the queue gets saved in LRU cache. LRU is nothing but least recently used. It is also used to optimize the data structures over here. Nothing, it stores cross-section states, user preferences or tokens, long-term facts are all stored in LRU cache. In LRU cache, we can give a max capacity that you can have like 5 or 6 messages, nothing more than that. And in DQ, it's a sliding window technique, a sliding window algorithm, where new message then append to the right, which is tail of the queue, and if capacity gets filled, pop the last message from the queue. The OpenAI agent SDK ships a trimming session class that does exactly this using Python's collections DQ. It works like this: new message, append right in the queue, oldest pop left, which means evict the last message from the queue. LRU cache maps the user preferences and details, which is retrieved by O1 in capacity. No, not capacity, O1 in time complexity. This is exactly how OpenAI streaming session and Redis back session stores work in production. Here is the code. LRU code is very simple. You just have to get the key and push the key in the stack. Not the stack, the hash map. Both operations are O1, which is very blazingly fast. Then we have the third part, which is agent orchestration. Here we use DAG, which is directed acyclic graph. This is nothing but each node an agent or tool, where each node will be an agent or tool, and all the edges will be the agent can hand off to that one, which means there will be no loops over here. It is just one single call to each one of them, kind of parallel and sequential. If you see, router gives an entry that research agent and coder agent should work on this, which is parallel and working. As soon as they get the output, it will send to the guardrail, which is a sequential agent, both the things, and guardrail will give it to responser, where we will get the response back. Here there is much more in depth that we first have to topological sort the execution, then prevent infinite loops by depth first search, and finds parallel branches to run simultaneously by using breadth first search, which is a searching technique in graphs. If you see, the real use case is not real use case, the live example of this is LangGraph, which is an explicit DAG builder, where as soon as you create your nodes and edges, it's exactly this. Then there is Apache Airflow, AWS setup functions, Netflix conductor, all model agent pipeline as DAGs. The next is knowledge retrieval. Here we start with inverted indexes because for example, if we have millions of documents, we can't sit and search each and every document, right? So first we do an BM25 search in our whole document list, which is very fast. BM25 is nothing but batch matching 25 algorithm, which is widely used in keyword based ranking algorithm in information retrieval, which is like if you have millions of documents, first we will narrow down all the documents using a keyword search, that okay, there are like 14 or 15 documents which consist of this keyword, and then we will create a HNSW, which is hierarchical navigable small world, which is a layers of graphs, where first layer, like the topmost layer, will very sparse, containing like long range connections. So if you see a document, like our main keyword was Mumbai, right? So it will take the approximate nearest neighbor from the layer 2, which is very sparse. Then in the layer 1, which is very medium, very close to each other, it will go in the layer 1, then in the dense, and at the final layer it will say, okay, document found, the Mumbai keyword consists in these documents, and it will go with the cosine similarities. This is actually used in RAG systems right now, where you do cosine similarities to search an keyword or to retrieve some information from your database, vector database. So if you see layer 2, which is the entry node, which is a long range highway, then in layer 1 we can get the actual, that okay, this document, this keyword might be near this kind of vectors. Then at the layer 0 we get an actual vector, and we can see, okay, this keyword is in this document. There is a hybrid method also, that Elasticsearch first filters docs containing Mumbai, which is inverted index. Then Pinecone ranks by semantic similarity. Real stacks, exactly Pinecone or Quadrant. If you have built rack system, then you have worked with Pinecone and Quadrant, which uses exactly this thing. This is the code for this. The next step is tool scheduling, which is a priority queue technique where you create a binary mini heap, which is a binary minimum heap structure where where the root node will be always less than or equal to its child node, and which will tell us that okay, this is the maximum priority here. The structure looks like this. The root node will be always less than or equal to its child node. So the agent decides each tool call becomes a task object with a priority number. They go into priority queue. Priority queue is binary minimum heap, a complete binary tree where every parent's priority is less than or equal to its children priority. The minimum priority is the most urgent and is always as the root because we should be access it very instantly. So as soon as we insert a task, we have first guardrail checks, which is the priority one. So we can give a priority number to every task that which should be the if the priority number is like less than, then it should be performed and it should be the root node. Now we extract the minimum from here. So guardrail check is the first very important task, so we perform that. Then whether agent we should call, then we should perform that. Then db query, similar for pdf generation and log events. Here heap always gives guardrail checks first, safety before everything. After it completes, whether API bubbles to top and so on. You have seen it over here. As soon as we extract the minimum bubble, whether agent bubbles up on top. Celery, RabbitMQ, AWS SQS, all of this uses this priority queue thing. The complexity of inserting and bubbling up is O log n. When we extract minimum from the nodes, it's also complexity is also O log n, and peak at the top. We just have to read the element, so it's O1. The next is async tracking, which is a hash map of futures. Futures is nothing but a keyword for concurrent tasks. So if you see futures in hash map Python. In Python there is a different keyword called as async if you have worked with, but you can also go with future. It's nothing but an object that says that I will have your result soon. As soon as the result comes in, it will just replace itself with the result. In JavaScript or Java, it's also called promises, an object representing a result that isn't ready yet. So if we do all of this sequentially, it could take us like 5 seconds to call each tool and to perform each task, but using futures of hash maps, you can do everything concurrently, which is very fast thing. If you see it over here, as soon as the task gets completed, it will just map that okay, this future keyword belongs to this task, and look up in the hash map, which is again a O1 complexity, and result is stitched into the plan, and the response is given back. And the total waiting time is longest single task, not sum of the all tasks. So it is very fast. Then there is safety guardrails. Here it's again try plus aho corsic. Aho corsic automation is nothing but a try with failure link. So in try, if we get in failure that okay, the word is not completed, the end of the word is not here, it will just reset everything. But in its upgraded version, it will just roll back to a point where a new word can start by from there. So it works like this safety guardrails. If response contains API tokens, it will log the response from there. If response is containing a password, it will be blocked. So this similarly works when you put guardrails for for NSW work or adult contents and everything, we put a guardrail. So for that we use stripe plus caustic for this. OpenAI moderation endpoints like ML based contextual community guardrail frameworks, all of this uses this try plus regex uh, framework with ML nuances added to it, so it's very fast. And try check is like OM complexity. M is nothing but the length of the keyword. And at the last we have response assembly. So for response assembly we have a ring buffer, which is a circular buffer. For example, imagine a queue with 10 indexes where token arrives at the right index and token diffuses at the read index. And as soon as the response is coming from, like as soon as the response we are getting, we create a JSON parse tree which is built incrementally as soon as the response is coming from there. So we'll just auto stream and see how this works. So as soon as the response is received, we get JSON structure that okay, this is the answer, this is the source, and this is the configuration of this. This is the ring buffer we actually want. OpenAI structure output, pydantic or sort schemas validates post hoc after full response is completed, not token by token. Python iJSON is basically this pydantic way to OpenAI output structures. Always have a fallback for malformed streams. So like these are the main data structures used in AI systems right now. Yeah, thank you.